Okay, first speaker is going to be Jepsen. He's going to tell us about challenges to accumulation point amplitudes.
Yes, thank you so much. Good morning, everyone, and allow me to start off by thanking the organizers for putting together such a wonderful conference. But let me also thank each one of you for showing up here on a Saturday morning to attend my talk. Yes, so indeed this talk will be focusing on these accumulation point amplitudes, and so by this I mean string theory candidate tree amplitudes that possess this property that they have an infinite sequence of poles, or semi-infinite sequence, but one where this sequence now converges on an accumulation point at some finite value of center of mass energy, right? And these amplitudes they've seen a good deal of interest in these past few years, and there's also been some sort of generalizations of them. And an additional curious property is that they possess a branch cut, even though they're candidate tree amplitudes. And perhaps a comment on nomenclature. I see David Gross is not in the audience. I hope you'll bear with me. Sometimes I might just use the word amplitude instead of candidate amplitude, right? So here's what the reggae trajectories look like. You'll notice instead of having the usual linear ones that are familiar to us, they bend and approach then this. So this is the value where you'd have S infinity. And then from this value, the branch cut emanates. Yeah. And so it's not known. So this is why I was talking about candidate amplitudes, right? There's no known physical theory by which you can derive these amplitudes. And it's also, they've passed some number of unitarity checks, but those checks have not been exhaustive. So the problem of exactly what to make of them is still an open problem. But of course, it would be nice to resolve, if we really hope to carve out, the space of unitary S matrices and string theory amplitudes in particular, right? We would like to know where exactly, if at all, these accumulation point amplitudes fit into the picture, right? So the Kuhn amplitude, that was like the first one. So sometimes I'll just refer to the Kuhn amplitude, or sometimes the Kuhn amplitude and generalizations. So okay, here's what the Kuhn amplitude itself looks like in the form it was originally written down. Just a single year after Leniziano wrote his amplitude down. Right, so it's given by this infinite product, and it's symmetric in S and T, and so it's conveniently expressed in terms of sigma and tau. And now let me start off by noticing I'm using a slightly different notation than Grant was using in his talk, right? So he was what he called sigma and tau is the logarithm of mine. But since I'm going to allow these to assume negative values, that notation is not as convenient in this case. And also this sigma and tau, they're going to appear in basically every single slide. So maybe I should just write them down here. Right. So just in case you're forgetting. But I mean, loosely speaking, you can just think of sigma and tau as S and T. So they're just linear or anti-linear functions of the Mendelssohn invariance. Okay, and so then we have this parameter Q. So that's some real number, a real continuous number between 0 and 1. Okay. And so the number of parameters, so the Kuhn amplitude, it's a function of two variables, S and T, but it has three parameters. So two parameters enter directly. We have Q, and then we have the mass squared. And then indirectly, it depends on the number of space-time dimensions in the ambient space-time if we attempt to do a partial wave decomposition. So okay, so let's look at the poles of this amplitude. We can read them off directly just from the denominator, right? And so it's a simple exercise. Right? I mean, you can see you have a pole when sigma is an integer, non-negative integer power of q. Just from the definition of sigma, a simple exercise, you derive that these are the values where you have the poles, right? And so they're spaced according to what are called the Q integers, right? So this is a generalization of the integers, which when Q goes to 1, this nth Q integer just goes to n. But when Q is less than 1, then they approach a finite value where this term just drops away, right? And so that means we have this accumulation point where the S channel poles converge on. And so in principle, in this first form, the Kuhn amplitude actually has non-polynomial residues, right? And this usually is something we don't want, right? Like because on a pole, right, we have some exchange of particles, and we prefer that to be a finite number of spins being exchanged, right? Otherwise, if you have an infinitely many number of spins, right, then somehow would require you to have an infinitely extended object, right? To not have some infinite deformation in a finite region. But so yeah, basically just by canceling factors between numerator and denominator, you see that actually in the original form it's polynomial in 1 over tau instead of being polynomial in t, right? But so Kuhn and collaborators they found a fix to this where they introduced this extra prefactor. So the prefactor it's symmetric in S and T. Then it has this property that you can just check, right? That when you evaluate it on a pole, so you set sigma equal to a power of q, then this itself becomes a power of tau, precisely such that this becomes a polynomial, goes from being a polynomial in 1 over tau to being a polynomial in tau and t. Okay. And then so I refer to this as like a deformation of the Veneziano amplitude, right? So in the limit when q goes to 1, you recover the familiar Veneziano amplitude. And perhaps I can one possible question you might have, which I can sort of preempt, right, is that why would you introduce this factor? Why not just change sigma and tau to 1 over sigma and 1 over tau, right? That would be an alternative fix. And the reason you don't do that is that you can very quickly check that if you do that, then you get the partial wave decomposition. You get negative partial wave coefficients, right? So that's you can very quickly see that's non-unitary. So that's why instead you introduce this factor, but it comes at a certain price because basically this prefactor is what gives the amplitude its branch cut, right? Which is gonna play a big role in today's talk. Okay. And now just a little maybe a bit of an aside is that you can also express the amplitude in terms of the so-called Q-deformed gamma function. And that's another way to understand how it has the nice residues, right? It's because just like the usual gamma function, it has sort of a nice recursive property, and it also has poles at the non-positive integers. Yeah, it's to the best of my knowledge, these two UCLA grad students who first wrote it down in terms of these Q gamma functions. Now, there was this work here by Simon Kahnhuro, Sohako Magotsky, Amit Sever, and Sasha Siboyedov that basically under pretty mild assumptions, the string theory amplitudes you can get, or more precisely, the only amplitudes with spins greater than 2, they will necessarily have to tend to the Veneziano amplitude, at least in this limit when S and T is large. Okay, but the Kuhn amplitude is and its generalizations. They're examples that do not meet the assumptions that go into this theorem. I mean, because they're non-meromorphic, right? Both by having an accumulation point and by having a branch cut. But it was pointed out that they do satisfy the positivity conditions on the poles that you would expect from unitarity. And so over sort of the last year and a half, there were several authors who started looking more closely into these positivity conditions and sort of chart out in the space of Q and M and D, charting out what the space where the positivity is satisfied on the poles. And also you can check the Wilson coefficients are compatible with causality. And then it's been known since the very beginning, right? It has the sort of the nice benign high energy behavior that we want for string theory amplitudes, in the limit of large S and T, and also in the fixed large absolute value of S, like large center of mass energy, both Regge limit and fixed scattering angle limits. Okay, and then finally over this past year, there have been a number of proposed generalizations, both some discrete generalizations that sort of shift around the locations of the poles and the first, like how the spins lie according to on the first poles, but then also these continuous generalization that Grant Remen told us about in his nice talk on Wednesday. And let me also just clarify that this talk only applies to these amplitudes that have a Q in them, that have this accumulation point spectrum, right? Because Grant talked also about like a version that just has an R, right? So that still has the usual Veneziano poles. So my talk has no bearing on that proposal. All right, yeah. So the open question remains, what exactly we're to make of these amplitude, right? And we also heard in his talk on Wednesday, they suggested one possible picture for how they could arise in terms of amplitudes on D-branes in AVS. So at least one thing that's noticeable is that these proposals and generalizations, these accumulation point generalizations, have only been proposed for as deformations of Veneziano. There's like the authors specifically state that they didn't find them for Virasoro Shapiro. Right, so it seems like, oh, possibly the string endpoints might play some key role indeed, because people haven't been able to deform fine annotations of the closed string amplitudes. Okay, but yeah, also the other question that was sort of open was if the amplitudes also satisfy the positivity conditions that must be satisfied for the branch cut, right? So for the rest of the talk, that's what we'll look into. So we'll perform this additional check. So let's just take a brief recap of what exactly are these positivity conditions I'm talking about, right? So of course, yeah, we're all familiar with unitarity, and then in this case, because we're now dealing with what I proposed as just perturbative amplitudes, right? Sort of leading amplitude in the perturbative expansion, right? That means that all we can get, right, once we go into this diagonal basis in terms of partial waves that you use Gegenbaum polynomials. So for that, this right-hand side is I mean, it's an absolute square, so it's positive, right? Like we can't say any more than positive because we're just doing perturbation theory. Okay? But yeah, the upshot is just, whenever we have an imaginary part, that has to be related, then that has to decompose into something that's positively weighted. And so yeah, here again, if a reminder of what the Kuhn amplitude itself looks like, right? And then we pick up an imaginary piece both on the poles, that's just arising from the I epsilon prescription due to this distributional identity. But then this extra factor, right? Like there are several ways we can write it. But basically, if we think of it as sigma raised to some power, which, for generic values of tau is not going to be an integer, right? Then it's clear enough that this expression here itself has a branch cut for negative, when either negative sigma or negative tau, right? So that gives us an extra imaginary discontinuity, right? And so decomposing these imaginary pieces into partial ways, we want the coefficients to be positive, right? And so in principle, if you just looking at the poles of an amplitude, you're in a sense only looking at a measure zero subset of the total set of conditions, right? Because this is just a discrete number of conditions. Whereas on the branch cut, right, it's sort of a continuous function you have to check. Plus also, the sum over spins can extend to infinity. Right, but so before looking at the branch cut, let me just, first both providing just a slight caveat, right? Because in principle, unitarity applies to the full amplitude, right? So and yet nonetheless, so far we've just been looking at a partial amplitude, right? It's a function that's symmetric with respect to S and T, right? So usually, like in Veneziano's first paper, right? Yeah, you add them all three together. But the Veneziano amplitude itself satisfies positivity already at the level of the partial amplitude. Right, and so I mean, in a sense, that's why you can put Chan pattern factors at the end of the string endpoints, right? Because the unitarity doesn't rely on a subtle cancellation; they are unitary separately. So that's the same case, for the Kuhn amplitude. People assume it exists already at the level of the partial amplitude. And so, okay, I just 2 slides to sort of summarize what are the constrained, what are the allowed regions from the poles. Yes. This one? Well, I mean, I guess you can say it's an empirical observation in the case of Veneziano, say. So, right, but, I mean, you said 14 you can, yeah. So maybe it's sort of a disclaimer that there, if now I start to point out some violations of positivity, this might be a possible loophole. But at least it's not a loophole that's realized for any of the other string theory amplitudes we know. So do you want to say right? Yeah. Right. Right. Yeah. Oh, yeah. And so for the Kuhn amplitude, so what usually happens, right, is that you get the strongest unitarity constraints just looking at, usually it's just from the first residues, right? So for example, you get the critical dimension 26, right, just by looking at the first non-constant residue of the Veneziano amplitude, or d equals to 10, the same thing for the super amplitude. So in the case of the Kuhns, these are the 2 bounds. These are the 2 first the 2 first coefficients you get in this partial wave expansion. And so from that we get these bounds on the mass squared. Okay, but then so in principle this expression here, right, Q is between 0 and 1, right? But in general, this left-hand side is less than -1. And usually the literature hasn't really looked at the regime where the mass is less than -1. Like it's kind of an exotic regime because you'd have multiple tachyons. But basically, okay, so basically it's just the point is that so just the two residues we just looked at, they give us these two bounds. They give us an upper and a lower bound on the mass squared as a function of Q, right? And then basically what this paper showed was that so they had an analytic proof that in this regime here that there's sort of a curve, and on the left-hand side, the positivity conditions are satisfied on all the poles in any number of dimensions. And then in this regime, it's satisfied only below a certain critical dimension. That's going to depend on where you're located in this region, right? So I stole this figure from them. Okay. So basically, this is the space of allowed regions we have left. In principle, also the purple region. And now, so what we're going to do now is we're going to see, okay, but what's left now once we start looking at the branch cut? Okay. Right. So yeah, here just, simple exercise just to write down what the branch cut is equal to. And now it turns out like you could just try sort of, do some like quick numeric checks. And I'm sure people did this, and indeed it does look positive. But it's going to turn out there are some like very well concealed numerical effects. And so for this reason, it will be advantageous to try and look at this from two different angles, both trying to get sort of a partial analytical handle, and also to try and flesh out what is the region where what is the region that most severely restricts the allowed values of the parameter space. And yeah, so we're going to look both at the forward limit, and then having some idea of where to look, then we'll perform some brute force numerical checks. So okay, yeah, if we start with just analyzing the forward limit, right? And so the idea here is that these partial wave coefficients, right? Like, sorry, the partial waves and their coefficients. So written in terms of, so theta here it's the scattering angle in the center of mass frame, right? So the point is that just simple as like a mathematical property of these functions, right? If you evaluate them at unit argument, then these polynomials and any number of derivatives will be non-negative, right? So that means that similarly, if we were to differentiate this expression here with respect to cosine, right, any number of times, and then evaluating at cosine theta equals to 1, that's to say the forward limit. So that's also when chi is 0. If we do that, then we still should get something positive, assuming unitarity, right? If these coefficients themselves are non-negative, right? And then, so in principle, we'd have to differentiate the discontinuity with respect to theta, right? And then, just we pick up, just the chain rule, this extra factor. But you can just check, right? Both because we want to be situated on the branch cut, and also we want to assume unitarity, right? So we're going to, we have this constraint from the pole. So on those constraints, this thing will automatically, this extra prefactor will be positive. So really, this is just what we have to check. Yes, and so, but there's sort of a zeroth order question you have to ask first, right? So the point is, before we even ask if we have, these positive coefficients, we should ask if this discontinuity, this imaginary, if we even have just a purely imaginary discontinuity. And so the issue is that actually this version of the Kuhn amplitude has a double branch cut, right? In the sense that you run into trouble when both sigma and tau are negative. Then you start to get something that's not just imaginary but complex. And that in itself could be an issue, but it certainly is an issue if that happens in the forward limit, right? So the very first thing we have to just impose is that in the forward limit we want tau to be non-negative. Okay, and that gives us this constraint, which in principle, depending on the value of Q, already restrains a bit the region, the allowed region we looked at already. But okay, so now we move on. So just you can just look at this discontinuity itself and see when it's positive. That's a fairly simple exercise, right? Because the overall sign is determined by this sign function, and also by this factor here, this factor in the denominator. And in principle, they both change signs when you have when tau is a positive integer of n, but when tau is a negative integer of n, then this sign function starts to change sign. And that means it's, and so this one is going to flip back and forth between positive and negative and give you some forbidden regions, right? And so these conditions on tau, once we take the forward limit, we can translate those into conditions of the mass as a function of Q. Okay, and so just plotting it's going to look like this, right? So these are the forbidden bands I just told you about. The purple region, that's the region where we have tau, where tau is negative in the forward limit, right? That's like this complex region that we don't want. But basically, if you look, the dotted blue lines here, those are the upper and lower bounds we got from the poles, right? Then pretty much everything is still allowed, at least in the regime of masses that the papers were focusing on. So nothing has been forbidden. Okay, but now once you take a derivative, yeah. So yes, that's right. So in principle, you also have the tachyon-free strip here between the x-axis and the dotted blue line. That's right. So Q going to 1, then the Veneziano amplitude sits right here at this corner. So what was the question? Yes. Oh, I am allowing for tachyons. Yeah. I'm taking the Veneziano to be okay, as just being, you're not sitting at the minimum of our potential. Yes, at least from just looking at the poles, yeah, it appears, right, that once Q increases the allowed values, yeah, you get more allowed values. That's true. But now we're looking at the branch cut, so then this might change. And in fact, I can reveal it will. But yeah, basically, just we all know how to differentiate. This is what you get, and this basically just looking directly at the derivative, it's kind of hard to see if it satisfies positivity or not. Basically, the regions is that you have this cotangent function, but also these Q deformed digamma functions appearing. Like, it's not surprising you get Q digamma functions because you're differentiating Q gamma functions. But the point is, in a sense, right? Like so for example, if we just look at the gamma function itself, right? It's at positive arguments, it's very well behaved. It's smooth. Its derivatives are smooth and monotonic, right? It's just a factorial function. But for negative arguments, it keeps flipping sign. So really, what we'd like to do is we'd like to flip, we'd like to flip these functions to the regime where they're nice. So basically, what we need to use is a Q analog of Euler's reflection formula, allowing us to switch between positive and negative arguments. And that comes at the price of introducing these extra functions, which are basically like these Weierstrass quasi-periodic functions. So the reason elliptic functions appear is basically, when we have these arguments appearing inside an exponent of Q, which means in principle, if you look at this factor, it's going to be periodic in the imaginary direction with periodicity 2 pi over log Q. Right, so that's why we start to get this second periodicity and why elliptic functions appear. Okay. So it just happens that then when you flip, you use this reflection formula, you get sort of a cotangent, which is just that's the same you'd get for the usual gamma function. But suddenly you also get these extra terms, these extra sinusoidal terms, which have coefficients that are actually extremely strongly suppressed in Q. Right. So if Q is some number of order 1, right, then you get these tiny coefficients that are like multiplying with sinusoidal functions. Okay, and it turns out that these functions are actually going to be the main key players in the story, right? And so sort of a reason why you have this unnatural smallness is basically you have sort of a modular relation, right? I mentioned elliptic functions, right? So this is sort of looking in the case of a rectangular lattice. This is sort of swapping the x and y axis. And so that you have a relationship basically between Q gammas and Q prime gammas with this relationship between Q and Q prime. And so, if Q is greater than something like 0.002, right, then 1 will dominate much over the other. Okay, but so basically, yeah, just using this identity, we get now nice smooth functions, the analog of having the gamma function at positive arguments, right? But then we have these additional sinusoidal terms. Okay, and what we can see already from this expression is that we want the right-hand side to be positive. And so to get the sharpest bounds, basically we need to take the limit where absolute value of sigma goes to 0. So we need to take the limit. So basically the positivity constraints are the sharpest if we go to the branch cut and we go all the way down right at the accumulation point. And then the dependency on sigma will just be via this in this periodic manner. Okay. And so then, okay, so let's just plot now what are the allowed regions. So the point is, when Q is very small, then these coefficients I showed you, they start to matter. And actually it becomes negative for any value of Q, right? And so in principle, for small values of Q now, like there's no value where the Kuhn amplitude satisfies the positivity conditions. So this was, so looking just at the first derivative. But now the point is, once we start to take more and more derivatives, we sort of this terms we sort of get more and more rid of this term, whereas the sine functions, they just keep flipping between cosine, and sine. So basically, you start ruling out more and more and more the more derivatives you take. And so in principle here, it's like it got a bit, the functions involved got very complicated, and also to go to the required numerical accuracy to reliably see what's allowed. So eventually I had to stop after 8 derivatives. So you might hope that there might be some remaining region that's allowed, but yeah, so we can address that now using the other method. And so the idea here is that we can also get these coefficients just by using just through numerical integration, because of just using these Gegenbauers. They satisfy they have this orthonormality relation, right? So you can just multiply the discontinuity with a Gegenbauer, and then you integrate to single out a coefficient, right? But then now we've learned that the regime where positivity might be violated is the region right above the branch cut, right? So basically, the idea is that we want to use then for this discontinuity, we look at the asymptotic regime where the dependency on sigma up to some overall function is going to be this periodic behavior. Okay, so basically what happens when you compute these Gegenbauer coefficients is that they start out positive as you'd hope for, but eventually they become small enough that you start to see these sinusoidal terms, right? And as you go higher and higher in the spin you look at, eventually these coefficients start to dip into negative values, and so the positivity is violated. Okay. And now, so the example I just showed you now, right? That is a general behavior you see, across different values of m squared and q and d. You start positive in order 1, but eventually you start to see the sinusoidal terms, and eventually you get negativity. Although sometimes, right, the greater q is, the higher you have to go in checking these partial wave coefficients before you see the negativity. But eventually, all the examples that you can try and look at least in my case, you see the negativity appearing. All right, so since I'm running out of time, let me just provide a brief summary and outlook. In fact, the summary is quite simple, that the Kuhn amplitude in its current form doesn't satisfy the positivity conditions we would expect from unitarity. Right, so this seems to present some challenge to the picture where you have some smooth, continuous family of amplitudes that interpolate between like scalar amplitudes and the Veneziano amplitude. Yeah, and so like the worst case scenario, you could just say that it's not unfamiliar, right? That once you try to take some function, you have some unitary amplitude or unitary theory, and you try to do a continuous deformation, and then there will be non-unitarity, also which is non-hidden, like in the case of say evanescent operators, right? Like if you try to do continuous number of dimensions, or you could try to take like an ON model with continuous n, right? And you can get these operators with complex scaling dimensions that Igor dubbed spooky operators, right? So that's like the worst case scenario, but maybe we can also end on a slightly more upbeat note in that, when you construct these amplitudes from the bottom up, right, there's actually some degrees of freedom you have left over on how you define them. Because, these papers that constructing the amplitude, candidate amplitudes from the bottom up, right, they look at the poles, right? But if you look at any function at just, a discrete set of values, that doesn't fully specify the function, right? You could always imagine you add some extra periodic terms that, don't contribute at that discrete set of points, right? And so in the case of the Kuhn amplitude, you could imagine that you multiply it with some extra function like this, which, it's a quick check that on the poles, you get cancellations and don't change the amplitude. And indeed, these kind of periodic terms are indeed what we see cause the terms of this form are what cause the positivity violations in the first place. So it's possible that there may be a fix, right? But so the unitarity is so powerfully constraining, right? That if there's a fix, it pretty much has to uniquely specify the function and not leave us with any degrees of freedom left over. But so hopefully in the near future it will be found out that there is such a fix, and if it's not found out, then probably over the next reasonable amount of time, then probably there isn't a fix. So we'll see what turns out to be the case. In any event, thank you for your attention.
Vision. The fact that this amplitude is not very wanted, the sun amplitude was supposed to be 3 level up, it is a 3 level amplitude, and then in here there is a branch cap, so it's not a 3 level amplitude. Let's say it's not positive. How is it going to think about?
Well, yeah, I mean, the hope would be that then it could point to some new physics. The one with Maldacena. Yeah, this is the brain picture with scattering in ADS. Right. Yeah. I mean, because it's certainly the asymptotic behavior, right? Where you have like where it's like, I guess it's like log A is some negative number, right? And then log S, log T, right? So, I mean, the exact amplitude hasn't been reproduced, but at least this asymptotic behavior, right, does exist for what is definitely.
What people call part of
Yeah.
So there is no pole. But just imagining some interpretation, right? Because normally you would say that the imaginary part dissociates and it's like what they were saying is that there is NG3 brains and you separate out one. Yeah. Right. So the dissociation has to do with making. So there is a intermediate states, right? Right, but then have a unitary accumulation there as well, right? But imagine touch. So this modification that was in the second whole paper, it was just yes.
I think so. Yeah. Yeah. I mean,
Saying this guess is not good enough.
Yes, that's right. Yeah. I mean, it's a bit similar. You know, Grant's last paper with Clever Chung, right? In a sense, they also introduced this prefactor by hand, and indeed, like specifically say that like they are open, like there could be more extra ways of like extra degrees of freedom in what you choose for your prefactor.
You look at the terms can you interpret those terms?
Yeah.
What that part of the cup?
Right, and I guess the same with this this possible proposed like this possible fix with these extra. Yeah, so this I purely noticed on a mathematical level. I don't have any physical intuition or reasoning for why you would have these extra.
Since those type of states, right? This different metrics, and then it could be negative. I mean, so it could be interpretation involving states.
Right. I mean, I guess the hope is that you won't need any other physical states at all, right? If you find the right expression, that's the hope, at least.
The sum series that we find.
So which of them? This like Bn? I'm just checking out. You're asking about this sum that was like Bn sine. Yeah. So this one. Yeah. Basically, these coefficients decay exponentially. So it is. I mean, it is this sum that is convergent. Yes. Yeah. Yeah, in principle, you know, there's also, you know, when you do this forward limit checks, right? There are some subtleties, right? Because, for example, in principle, I omitted the slide with the technical details, but you're different. You know, you're commuting a differential operator when you take the forward limit, right? You're differentiating the Gegenbauer, so you're commuting an infinite sum with a differential operator. right? And that's only valid when you have absolute convergence, right? But you can check numerically that you do have absolute convergence. It is justified to perform this commutation. Yeah.
Checking the poll, that obviously the other muscle channels cannot possibly increase the emission.
Right, you're saying adding together. No, I don't think it's obvious. It is, I think it hasn't been explored, like ruled out as a possible loophole.
One that was just pushing features because SMT seem to be, right?
Yes, yes.
What about future?
Right, yeah. So for an actual amplitude, you need to add together, you would have the amplitude as a function of S and T and then add together S and U and T and U. You'd have to add the full sum together, yes. That's right.
So this is where future is okay.
And
No, I mean, because like Raymond was talking about for him, if this going to future will very much additional constraints.
okay, yeah, I think, I mean, in this case, if you could say that like the imposing unitarity at a partial amplitude is more restrictive. So in one sense, it's like almost the requirement here is too restrictive that we're just looking at a simple channel. But if the single channel does satisfy, then the sum will satisfy. Yeah.